Hello and welcome to this part of Advanced Materials Chemistry course, which is Functional Materials Part 2. And mostly we'll be seeing device-worthy materials in this. So, as we know, most of the devices we use semiconductor materials, and therefore it is essential to understand the basics of semiconductor physics. So this lecture is dedicated to fundamentals of semiconductor physics. Let us see what is the syllabus of this lecture. So first part is photovoltaics, which includes solar energy and energy conversion, fundamentals of semiconductor physics and photovoltaic cells, generation recombination in semiconductors, PN junctions, metal semiconductors, and heterojunctions, photovoltaic device fabrication and characterization, current status of silicon-based solar cells, advancement in photovoltaic research and design of new generation solar cells. Then we'll see thermoelectric materials, fundamentals of thermoelectricity, Seebeck, Peltier, and Thomson effects, thermoelectric effects and transport properties, basics of thermoelectric devices, heat conduction in bulk thermoelectric materials, progress in thermoelectric materials, nanostructure thermoelectric materials, reduction of thermal conductivity in bulk and nanostructure materials, and thermoelectric devices. Then we will see some device-worthy materials, which includes important elemental and compound semiconductors, which are germanium, silicon, tin, tellurium, and amorphous silicon. Single crystal growth techniques, float zone, Czechoslovsky, hydrothermal, different kind of you can say growth methods, and like thin film deposition techniques also you will see. So as you see, all of these devices use semiconductor. In fact, majority of the devices available in the market or anywhere, they use semiconductors, because in semiconductor materials you can actually control the different properties or electronic properties of the material. You can fine tune the properties, and therefore these materials are used in the devices. So then first question comes, what are the semiconductors? So semiconductors are solid state materials. In general, solid state materials can be grouped into three classes, which are conductor, insulators, and semiconductor, based on the electrical conductivity. A substance that conducts electricity is called a conductor, and that does not conduct electricity is called an insulator. It's a very simple definition. And then the semiconductors are those substances where the conductivity lies between the good conductor and that of the insulator. So there are actually two properties semiconductor possess. Number one is their conductivity, which lies between insulator and semiconductor, and there is another you can say property which says the temperature dependent conductivity. So as normally in metals, as you increase the temperature, the resistivity increases or conductivity decay. However, in semiconductors, as you increase the temperature, their conductivity increases. So semiconductor are those materials for which the electrical conductivity lies between insulators and metals or good conductors, and their electrical conductivity increases with increase in the temperature. So if we see typical electrical conductivities of some important materials in all of these three classes, we can see here on this chart. So if you see this side, we have good electrical conductors, which are silver, copper, aluminum, platinum, and bismuth. And on this side of this chart is good insulators, which are glass, nickel oxide, diamond, pure. and fused part like. So if you can see, the resistivity of good insulator is between 10 to the power 18 to somewhere here 10 to the power 8. Similarly, the resistivity of good conductors lies 10 to the power minus 8 ohm centimeter to around somewhere there. We can say there is no exactly, you cannot say a particular number where you can differentiate, but it is a range. And there are materials which are having electrical conductivity between these two, and these are the semiconductors, and we are interested in these materials. So this is resistivity, and if you see in the lower, you can say we have plot conductivity, which is just opposite of the resistivity. So it is 1 upon resistivity. We can call it as a conductivity. So if it is like here, it is 10 to the power minus 8. So you can say 10 to the power 8 is the conductivity, and the unit is Siemens per centimeter. Now, since everything depends on the electrical conductivity, so first let us understand what electrical conductivity is. Electrical conductivity is a result of movement of electrically charged particles. So, electrically charged particles can be charges like electron and some other charged particles, ions, and it can be in liquid, it can be ions also. So however, in solid substances, the movement of free electrons causes conductivity, because generally in solid state, ions movement is not there, unless in some other advanced materials, if we say where ion movement is there, because that ion movement in those cases also facilitated under certain conditions. So now you have free electrons which need to be moved. So how these free or why these free electrons moves? Because these moves under an influence of an electric field. And how this electric field is generated? What is electric field? When you apply a potential, there is an electric field E, which is simply V by D. If there is a distance between two plates, D is the distance, and you applied a potential V. So because there is now electric field, so every charged particle inside an electric field experience a force which is Q into E. Here, because it's electron, so it is E into E. Now, next questions come, can pure atom behave as a good conductor? Like we know, gold is a very good conductor, or copper is a very good conductor, silver also is a very good conductor. Suppose we have a pure atom of silver, will it conduct? Do you have any idea? Will it conduct? Suppose I have pure silver atom, will it conduct? Or gold, which is a very good conductor, or copper. So because every atom, all the electrons are bound to the core, and therefore there is no free electron available. So even if you have like atom of gold, silver, or copper, which are generally good conductors in you can say bar form, in atomic state, if they are there, there will not be any conductivity, because conductivity is because of presence of free electrons, and normally in all atoms the electrons are bound to their nucleus, and so they are not free. So pure atom will not be conducting. So what we have to do? So if we can somehow remove electrons from these cores, and then if they are free, or then make these movable, then the material can conduct. It's very simple. So you have to remove the electrons. Electrons should be removed, and then they should be mobile also. So now we have two important parameters. Number one is availability of free electrons, and number two is their capability of movement. So these are the two regions for the electrical conductivity. So even if we have free electrons, but they are not mobile, then also there will not be any conductivity. And if there are no free electrons, then of course there is no possibility of any electrical conductivity. Now next questions come, can electron attain all possible energies? Suppose you have an electron and you have put under an electric field and you have applied a voltage and you are gradually increasing the voltage. Suppose from 0 volt to 10 volt and a step of 0.0001 volt. So if an electron is free, in that case, it's you can say energy will accordingly increase linearly as you are increasing. So it will be simply E into V. So when electron is free, of course, it can attain all possible energies. But when it is in a bound state, then there are only certain energies which are allowed. It cannot attain all the possible energies. And we will see it little later in today's lecture that what happens when it is subjected to a periodic potential. When an electron is subjected to a periodic potential, then it may not be possible that it can acquire every energy. So then there are only certain discrete energies are allowed. So now if we see different semiconductor materials, so this table shows a period of periodic table where semiconductors can be seen. So in dark yellow we have shown certain materials which are used in the semiconductor industries. So silicon and germanium, these are two straightforward semiconductors which are by itself they are semiconductors. So these are there, and then there are other elements like this side we have certain elements and this side we have certain elements. These are also used in the semiconductor industries. How about the silicon, actually, which is the most abundant material? It costs very, you can say, price is also very cheap. It can be produced easily, and therefore, majority of the industries, majority of the devices uses silicon as a semiconductor because it is quite cheap. And more important, its abundance. It comprises about nearly 27% of the Earth's crust. So it is, you can easily get silicon. So, and because of its availability and its useful properties, silicon is the most studied element in the periodic table. And the silicon technology is by far the most advanced among all semiconductor technologies because of its availability. And so many groups are working on this since the beginning. So one was like silicon and germanium. These two elements, they can be used. They are actually semiconductor in its intrinsic form also, without mixing with anybody. But then, so these are called as the elemental semiconductors. Then there are compound semiconductors. So because silicon has four electrons in the outermost orbit, and all these four electrons are bound to the nearest silicon atom, and then core is you can say completed. So then you have compound semiconductors. So a number of compound semiconductors have found applications for various devices. A binary compound semiconductor is combination of two elements from the periodic table. So for example, gallium arsenide. So you have from one side of like this. So it is like gallium and arsenic. You mix them, gallium arsenide, then indium antimonide, aluminum phosphide. So these are like binary semiconductors. Binary semiconductors means when you are binary compound semiconductor means when you are mixing two materials and then the resultant material is behaving like a semiconductor. So you have like from column 3 and column 5 elements. Similarly, you have different kind of other. You can use this like 3, second and 6 also. This like zinc selenide. This can also behave as a binary semiconductor. So different like binary compounds are 4,4, which is silicon carbide. That is also a binary compound, which is used in semiconductor industry a lot. Then other binary compound, aluminum phosphide, similarly aluminum arsenide. So one from this side, another from this side. So this kind of semiconductors are binary compound semiconductor. Then we have some ternary compound also, where like another element is added. One you can say element is doped. A suitable element is doped into like a binary compound. Like here you have aluminium gallium arsenide. So gallium arsenide was binary you can say semiconductor, and if you add a fraction of aluminium, then the compound is a ternary compound. Similarly, we have some quaternary compound also, which are like some examples like aluminium, gallium, arsenide, and TBT. So ternary compounds and quaternary compounds are made for special applications. They alloy semiconductor like aluminium, gallium, arsenide, which has aluminium, gallium from column 3 and arsenic from column 5. This is an example of ternary compound. Whereas quaternary compounds are of the form AXB 1 minus X CY and D 1 minus Y, where X and Y are the fractions. So suppose here, if I have like this aluminium and indium, the you can say doping is 50-50. So I can write aluminium 0.5, indium also 0.5, and then arsenide. So many of the compound semiconductors have electrical and optical properties that are different from the which is of the silicon, because so for those you can say different electrical and optical properties we need to have or we need to develop these ternary or quaternary compounds. So now what is the important thing which plays a role? Like all the atoms are almost similar. So crystal structure, when they are forming a solid, they form it in a crystal form. So in which structure they are crystallizing, that plays a major role in the device properties. So some of the you can say crystal structures you have already studied in the first part. So I will not go in detail with all those structures, but some crystal structures which are very important for the semiconductor materials, we will just quickly go through. So for that, we will see all the structures very quickly. So the semiconductor materials are generally single crystals where atoms are arranged in a 3-dimensional periodic fashion. This periodic arrangement of atoms in a crystal is called a crystal lattice. In a crystal, the atoms are at fixed positions. So there is something called lattice. Lattice is nothing but it's an array of you can say infinite points. Nothing there, only the imaginary points which are arranged in a regular fashion and which fills entire space. That is a lattice. When you put at each lattice a particular basis or atom, it can be atom or it can be a molecule in a certain you can say following an exactly symmetric structure, then this becomes crystal. So at absolute zero, there is no vibration. All the atoms remain at the fixed positions. However, as you start increasing the temperature, the thermal vibrations takes place, And why this thermal vibration takes place? Because of the thermal energies associated with the atom at higher temperature. So then all the atoms, they vibrate around their mean position, which is this particular point which we are talking about, a lattice point. Then in the lattice diagram, the lattice point we display as a dot, but these are actually imaginary points. Dot we are just we display only like so that we can recognize, okay, this is our lattice point. Otherwise, in lattice, actually these are imaginary points. And then the structure is repeated by translation. So you have a lattice. Lattice means a set of imaginary points. At a particular, you can say in a certain fashion, and then you fix a basis, which can be a molecule or atom, and then you just repeat it at every with a certain translation in all x, y, z direction. So the lattice has a translational periodicity. What is that? So suppose this is a translation vector T, and how we can represent it is U1A, U2B, U3C, where U1, U2, and U3 are integers, and A, B, C are translation vectors towards X, Y, and Z direction, or any three directions. So then we have 7 crystal systems. This you must have already studied in the first part of this course. And these seven crystal systems, and then there are 14 Bravo lattices. So crystal lattices can be classified by their translation and rotational symmetry. In 3-dimensional crystals, these 3 symmetry operations yields 14 distinct lattice type, which are called as the Bravo lattice. So why these are formed? Because of the symmetry operations on a particular point. What these symmetry operations are? They are translational and rotational symmetries. So for a given crystal, there is a unit cell. What is unit cell? It is a representative of the entire lattice. And there can be many unit cells. So like you have a smallest cell, and then if you add 2 smallest cells, that can also be a unit cell. But the smallest unit cell, which contains only one lattice point, is called as the primitive unit cell. All other are called as the unit cell. So unit cell as such it can have many primitive cells also, like 5 cell also, you can add them together, that will also become a unit cell. So as such, unit cell is a simple volume which you keep on adding, and then all the 3 directions, and then you can make generate the entire volume. So that can be possible by having any you can say volume, integer volume of the primitive unit cell. However, the primitive unit cell is that unit cell which contains only one lattice point. So by repeating the unit cell throughout the crystal, one can generate the entire lattice. Now, as far as the semiconductor materials are concerned, mostly cubic structure is important. In some cases, hexagonal also, that is wood-jite kind of structures. But we will just see some cubic structures which are important for us. We should just keep in mind. So cubic is, as we see here, so this is cubic. It has 3 Bravo lattices: simple cubic, body center cubic, and face centered cubic. And what are different parameters for any lattice which need to be known in order to describe that lattice? These are you can say 3 axes. You can say in these 3 axes, that is A, B, and C, and then alpha, beta, and gamma, which are the angle between the opposite axis. Suppose A, then angle between B and C is called as alpha. So now for defining any lattice, you have three important parameters, which are A, B, C, and alpha, beta, gamma. These are the angles. So this cubic structure has three Bravais lattices. One is simple cubic, another is body-centered cubic, and third is the face-centered cubic. In simple cubic, if we can see, it is like that. You have like here 8 spheres, and all those 8 spheres, if you can join their centers, you can see a structure like this, or this is a cube. So in this, what we have A, B, and C are, you can say, equal, and so we can call A is equal to B is equal to C, and this is equal to A, suppose. So we have lattice parameter A, B, C equal to A, and the angle between these axes is also 90 degrees. So alpha is equal to beta is equal to gamma is equal to 90. So this is for simple cubic, and in fact all cubic. So one is simple cubic, another is BCC, that is body centered cubic. So in body centered cubic, we have atoms at all the corners, and there is one atom at the center also, center of this cube. That is the center of this body. So we have like atoms at all 8 corners of this cube, and one atom at the center of this cube. So this kind of structure is called as body-centered cubic. And in face-centered cubic, you have like parameters are same. So you have a cube, and there are 8 atoms at each corner, and then at each face you are having one atom. So in face-centered cubic, you have atoms at each face and at each corner. In body-centered cubic system, you have atoms at you can say each corner or this edge, and at the center. And simple cubic, you have at the edges only. So this is what I have just explained. So each atom in simple cubic has 6 equidistant nearest neighbors. The dimension is A is called as lattice constant. Polonium is crystallized in the simple cubic lattice. In a body-centered cubic system, where in addition to 8 corner atoms, an atom is located at the center of the cube also. In BCC lattice, each atom has 8 nearest neighbor atoms, and crystals exhibiting BCC lattice includes those of sodium and tungsten. The face-centered cubic, which is actually a very, you can say, one of the very important crystal structure. It has one atom at each of the 6 cubic faces, in addition to the 8 corners atom. In this case, each atom has 12 nearest neighbors. A large number of elements exhibits the FCC lattice form, including aluminium, copper, gold, and platinum. If you see, these are like good conductors. So now when you have atoms, when they are crystallizing, why do they crystallize in different structures? Why? Because when they like, suppose imagine they are coming from one phase to another phase, or they are from liquid to solid phase. So there is a heat of transformation associated with each phase change. So that is called as the latent heat. So when they are actually crystallizing from liquid to or melt to solid, in that case, that heat of crystallization has to be released. And there is another important thing, that when every system want to attain the minimum possible energy. So if now when it is crystallizing or liquid becoming solid, in that case certain amount of heat of fusion will be released. So that latent heat, it has to be passed away from the interface to the outside or to the atmosphere. So it should be removed from the interface. If you can remove that entire heat, in that case, all those atoms will go and sit at the minimum energy positions, which is actually FCC. This we will see in the next slide also, how it is minimum energy position. But if somehow the conductivity or thermal conductivity is not that high of that material. In that case, it will not be possible to remove that entire heat from the interface, and therefore that will crystallize in some other form, like BCC, and in that case, simple cubic structure. So now let us see FCC structure. So how FCC structure? So let us consider all atoms as sphere, though they are not spheres, but in solid state physics, normally we can consider atoms as spheres. So suppose the atoms from the liquid state, they are becoming solid. So now they have a lot of time, so they will form a minimum energy kind of position. So they can now imagine they can when they come closer to each other, they can come in this form also, like one atom, second atom, and then the atom has suppose it was one atom, 2 and 3 atom. Now suppose fourth atom come. This fourth atom come at this place also. It has come at this place also. So the minimum energy position will be actually this. So like here. So this is one atom, second atom, and this atom has come here, joined. So there is a minimum gap. However, if you will see in this case, there is a more gap. So this is not the minimum energy position. So that means if some material is crystallizing in this form, so it is also one possibility that the entire heat of crystallization has not been removed from the interface to the other part. So some part has already remained there. So this atom, when it was crystallizing, it already possesses certain amount of energy, and this energy, this heat, and because of that, it has actually not come at this point and crystallized. So we can have see closed pack structures are like when it goes like this. So suppose one layer, you have different spheres, you can join them together. So one sphere, two sphere, three sphere, four sphere, then the fifth will come like 1, 2, 3, 4. So you can see this volume between two sphere is minimum. Now this is as far as the first layer is concerned. Now imagine the entire first layer has been completed. Now you want to add another layer over this layer. So where it should be the minimum energy position? It should be somewhere in like here in this gap. Similarly, in this gap. So you have three atoms, three spheres here, and the fourth sphere should come and sit here in this at this gap. This group, you can say, and there is a name for these groups. That is called as the you can say it makes a void. So then the second layer will be added over this, and then so now suppose you have one layer. If we see configuration A, and the second layer which has been added by putting the spheres over these groups, which becomes B. So there is only one possibility by which it can be added. Now when you want to add a third layer over this, so either you can put the third atom here at this particular point, or you can add in this particular you can say void or space, or you can add here also. So if you add here, you will be adding one sphere, and one sphere. So this will be then it will be like a third formation. So suppose this is A, this becomes B, and then it will become C. So it is actually a different kind of layer. So if you are stacking the layers in form A, B, A, B, A, B, you can add this also, A, B, A, B, A, B. This is actually hexagonal closed pack, HCP structure. And if you are adding a structure like when you are one layer, then another layer, and the third layer is also different than these two layers. I'm talking about the alignment, right? Just visualize. In solid state physics, many things are actually many of the things are you need to visualize in order to understand it correctly. So now you have one layer of spheres. You have put another layer of spheres in this form. So your groove is like this void over this void. This, and then you will add the third layer. If you add this third layer, which is not exactly the same like or you can say the third atom is not coinciding with center of this atom. In that case, that layer will be a C layer. And then fourth layer will automatically come exactly where the center of the sphere will actually be above this, exactly this. So then this will be A, B, C, A, B, C. This structure will be then FCC structure. Now, in last slide, we saw that actually FCC structure is face-centered cubic. So there should be some cubic, but here if we talk in these layers, there is no cubic actually. We are not able to visualize any cube. So if you see here, actually it is a cube. Now, suppose we come here, actually cubic should be like this. So suppose I am saying this as an FCC, and I am saying this also FCC, but these two structures are looking quite different. If you just see, here are actually corners, and then there are some atoms at the each faces 1, 2, 3, 4, 5, and then 6. So this is not actually looking like this. But if you see from this angle, or if you just turn it slightly lower, then you can actually realize that this structure and this structure are same. You have to little bit rearrange the atoms. So just see 1, 2, 3, 4, 5, 6, and 7 atoms. These are 1, 2, 3, 4, 5, 6, and 7 atoms, one in between. And then if you come here above, there's 1, 2, 3. So it is like 1, 2, and 3 atoms. So this way, if you see, you can understand that it is a closed pack structure. So closed pack structure is the most preferred structure, and it should be ideal structure when entire heat of fusion has been removed from the interface and it is a closed pack, and so there is a least possibility of the energy extra energy being there. Now there is a very important structure that is called as the diamond structure. Diamond structure is not important because diamond is expensive, but this structure resembles with the silicon structure or germanium structure, and therefore diamond structure. Therefore, in every crystal structure book, we study different structure. One is diamond structure, zinc blende structure, NaCl structure, because these are representative structure of their class. So now what is diamond structure? If we see diamond structure, it consists of two interpenetrating FCC lattice. Now what was FCC lattice? It was like this. So you have one FCC lattice, you forget the upper part, just ignore this part. So you have one FCC in which there are atoms at 8 corners and there are atoms at the each faces. Now you imagine just one FCC structure, and now imagine exactly identical FCC structure, same, exactly same. And so insert that FCC structure inside the first structure. How you will be inserting? So that the origin of, so the first FCC structure and the origin of the second FCC structure, that actually they are apart 1 by 4, 1 by 4, 1 by 4, means diagonally. So it is like you just, so you have one actually structure 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then these other atoms, Then there are certain atoms which are at the face, 1, 2, 3, 4, and then there will be one is this side and another, that will be another side. And then you will have another structure which has been inserted inside this. So just imagine two structures inserted, uh, uh, two exactly identical structures inserted one into other. Actually, it is not a Browell lattice. So, however, there are 8 unit atoms in the each unit cell. So, how we can say? So, suppose now we can call a basis. Basis means the unit which we are repeating at each lattice point, which is one atom at 0, 0, 0, and another atom at 1 by 4, 1 by 4, 1 by 4. 1 by 4, when I say 1 by 4, 1 by 4, it is in terms of the lattice parameter, which is A for simple cubic. Because A, B, and C all are same. So this, and these three have exactly same dimension, not dimension, but same size. So 1 by 4 or A by 4, A by 4, and A by 4. So you have one atom at 0, 0, 0, another atom at 1 by 4, 1 by 4, 1 by 4. So just you don't have to think too much. Simple, very simple way. Just have two identical FCC structure. Insert one FCC structure into another FCC structure in such a way that corner of one structure and corner of another structure, they are just apart diagonally 1 by 4, 1 by 4, 1 by 4, or A by 4, A by 4, A by 4 distance. So carbon, silicon, carbon when it is in the diamond form. Carbon has actually many structures, but here we are talking the diamond carbon structure. Silicon, germanium, tin, these crystallize in the diamond structure. And because silicon is the material or you can say crystal which is used in the semiconductor industry very much, and therefore this structure plays a very important role, because when you want to understand the properties of any material, you need to make many calculations, and on those calculations you need to have structure. You have to solve that structure. And then by solving then many different calculations, you applying those parameters, then you can actually predict the properties, possible properties of that particular material. And therefore understanding this structure is very, very important. Now, like for diamond, the value of A means from this distance from this to D is 3.57 angstrom, and for silicon it is 5.43 angstrom. So silicon, if you want to visualize the silicon crystal structure, it is exactly similar, where this atom is of silicon, and in diamond structure this atom is of the carbon. So there, this was one structure which was very important. You can just see, you see there are six blue atoms. That is the first sphere, and then there's one atom which you can see here, which are rotating. That is actually, these atoms are of the second lattice, which you have forcefully inserted. So this, by this way, it can be 0. That is in the next slide, I think so. So now, if you actually want to visualize how this structure is actually here, it is formed. So imagine you have, as I told you in the 2 slides before. So you have like 3 spheres, and you have put another sphere here. So the void which is actually created among these 3 spheres is called as the tetrahedral void. So you have 1, 2, 3, and you have the another sphere. So just imagine for the time being, now you have only 4 spheres. So you want to pack them very closely. So what you will do, you will put 3 spheres in this way, and then you will put the 4th sphere exactly above. Just visualize. Uh, uh, you have put 3 spheres. Visualize, because visualization is important in this particular case. You have 3 spheres. Now you have put one more sphere above those 3 spheres. Now the gap which is formed between these 3 sphere and the 4th sphere, that is called as the tetrahedral void. Now you bring another sphere, the 5th sphere, and somehow insert that sphere in this void. So what will happen? This will little move this side above, and you will have a sphere which is actually placed inside this. Understood? Now think again, once again. You had 4 spheres, and you wanted to make a closed pack structure. So it was a 3 sphere, you will put 3 sphere, and 4th sphere you will put like this. So this will become a FCC structure because it's a closed pack structure. Now in this closed pack structure, between these 3 spheres and the 4th sphere, there will be actually certain amount of gap. You can visualize that. If you आप 4 स्फीयर्स को एक दूसरे के साथ में इस फॉर्मेट में if you will add, there will be a gap between those 4 spheres. That gap is called as the void. So there is a name as tetrahedral void. If you will form like if you will add more, एक octahedral void भी होती है ना. So if you will have 3 sphere here, then the void which is formed, that is the octahedral void. So now if you want to make this diamond structure, just bring another atom or another sphere and forcefully insert between these two. These you can say these 2 layers. So अभी क्या होगा? This atom and this atom and this atom and this 4th atom, they will be, the center of these atom will be equidistant to the center of the atom which you have inserted or forcefully inserted between these 3. So अभी ये एक दूसरे के कांटेक्ट में नहीं रहेंगे. There will be little gap between these, and there will be little gap on the upper side also. This bond is also up. Now you will imagine the angle of this bond will be 109 degree, which we used to study like in methane and all those. So that is tetrahedral bond and that angle, because it is not exactly the same. So then this, if you will add the center, this is called as the tetrahedron without inserting. So now if we want to visualize that in a simple you can say 2 plane diagram. So you have 0, 0, 0, 0 positions. On these 0, 0, 0 positions, we have silicon atoms in silicon structure, and in diamond structure we have the carbon atom here. Now at the half, if you come above at half, this will be actually a you can say atom, same atom, carbon atom of the at the center of this space when you are coming up. When you are coming up in all these 3 directions, and so and then this 0 is actually at the face of this one. So white atoms are because of the first structure, first FCC lattice. These different atoms which are at 1 by 4, 1 by 4, and 1 by 4. So if you come this way, you can say here 1 by 4 and 1 by 4, and here you will have at further 3 by 4 up, means further half up. So these 4 atoms are because of the other lattice, which you have inserted in forcefully. So now visualize this way. At 0, 0, 0, 0, one layer of the atoms which are of carbon. Then you come little up. Then you will see these 2 atoms at 1/4 distance. We are coming in the y direction or up direction, whatever you want to call them. Then you will come further up. Then you will reach at 1/2. So you will have 1/2, 1/2, 1/2, 1/2 distance, same atom. And but it is because of the earlier one. And then you further come up. Then you will, when you will come at 3/4, 3/4, you will see 2 atoms. Then come above. When you will come exactly at the A, then you will see the same 0, 0, 0 layer here. Now, exactly similar kind of structure is zinc blende structure, and this is another important structure in diamond structure. If you understood diamond structure, you can understand zinc blende structure also. It is exactly similar. Only difference is, like in diamond structure, see what we did. We had one FCC structure and we had another FCC structure. We inserted the first. We inserted the second FCC structure inside the first FCC structure. So in such a way that the origin of the second structure is exactly 1/4, 1/4, 1/4 distance away. I am doing the same thing here also, but there is a small difference that where both the atoms were same, in here the atoms are different. I have one FCC structure of one particular atom. I have another FCC structure of another atom. But A, B, C, alpha, beta, gamma are exactly same. ABC means here ABC or are equal. So it is A is same, means the lattice parameter of the both FCC structure is same, and the angle is also 90. So you have two identical FCC structure. Only thing, the only difference is that the atom which is used in first is different, in second it is different. Now you do the same thing, that such that suppose you have the origin of the second FCC structure is actually 1/4, 1/4, 1/4 distance away from the origin of the first FCC structure. So this structure is called as the zinc blende structure. See, this is actually a structure of zinc sulfide, but zinc sulfide is not so important material that we should specifically study, or every student must study the zinc blende structure and should know about it. Why? So because there is other than silicon, there is another most important compound, gallium arsenide, which is also a semiconductor which is used, that crystallize in this form. So now just imagine, if I want to tell you zinc blende structure of this gallium arsenide, it is one FCC structure of pure gallium, imagine, and then imagine another structure of arsenic. There will be difference in sizes of like gallium arsenide, but ignore for the time being. You have somehow you have made the lattice parameter exactly same. Now you bring that structure of arsenic and insert FCC arsenic and insert that in the FCC structure of gallium. This will be formed as the zinc blende structure of the gallium arsenide. So it is gallium arsenide, gallium antimonide, indium arsenide, silver iodide, etc. These materials crystallize in this structure. So now you know the you can say points where each atom is sitting, and this plays important role, as I earlier also told, when you calculate the properties using the different calculation tools. So now just briefly, I will compare both these structures. So two atoms are the two are technologically important structure because many common semiconductors have diamond or zinc blende structure. They share the same geometry. In both the structure, the atoms are tetrahedrally coordinated because you have one atom. They see there were four. Just imagine that those four is sphere and forceful insertion of the three is fourth sphere and forceful insertion of the fifth sphere. In both structures, the basis set consists of two atoms, and in both structures, the primitive lattice is face-centered cubic. This we have understood well. And in both the diamond and zinc structure, there are two atoms per FCC lattice point. However, in diamond, these two atoms are of the same material, and in zinc blende, these two atoms are of the different materials. So now that was as far as the crystal structure concerned. There is one more thing which you must have seen at many places. There are different planes. We define these planes in the crystal. So what are those planes? What is lattice? As we saw in the earlier, lattice is nothing but that is the, you can say, collection of imaginary points which are ordered in a uniform fashion, and they fill the entire space. Now, when you add any 3 points in such space, you will make a plane. So, how many planes are possible? There are actually infinite planes are possible. So, all these planes inside the crystal structure are called as the lattice planes. So you have an ordered structure, ordered three-dimensional structure. You just make any, you can just join any 3 points and extend it in that particular direction. You will be able to make a plane. So you can have many number of planes. So these planes are very important actually. These planes play a very important role in the device fabrication part. So atomic spacing is different for 2 planes, though there are infinite planes. So obviously, if they are not, I'm not talking about the coplanars, means the planes which are parallel to each other. Even in such case also there will be infinite planes. So in any 2 planes there will be a gap. That gap is called as the interplanar spacing. So the crystal properties along different planes may be different. And if the plane, it depends actually what property you are measuring. Some properties are same, some properties differs. So you have some anisotropic properties also where it's a direction dependent. So the electrical and other device characteristics can be dependent on the crystal orientation. A convenient method of defining the various plane in a crystal is to use Miller indices. So we, because we know different properties which may be of a particular use for us, if that property is direction dependent, so we should be knowing that the material or the crystal which we are using or the phase which we are using to make a device, it contains which plane. So there is a way. So therefore, if you want to know the plane, first thing there should be a way to define or identify the plane. So to do this, we use Miller indices. So this they're very simple. You should be you should know only a few things. So if you have a plane, just find the intercept, because this any plane will cut this x, y, and z coordinate some z axis at some particular point. So find the intercept of the plane on these 3 coordinate axes or 3 axes. So there will be, you will get certain coordinates. Now take the reciprocal of these numbers and reduce them to the smallest 3 integers, which is having exactly the same ratio. So ratio is not changing. You are multiplying with some number, generally LCM, and then so that you can have the smallest possible set of integer numbers, and then just enclose that with this parenthesis, and these are called as HKL, and these are the Miller indices. I will just give one example just to very briefly to find out how to find out a Miller index. Suppose we have this plane, this yellow color plane, and if we want to can say find out the Miller indices or what is this plane. So this is actually at you can say x-axis, it is coming at 3a, y-axis it is coming at 2a, and z-axis it is coming at a. So now what we will have to do, this we know. So we will just do reciprocal. This is 3, it becomes 1 by 3, it is 2, it becomes 1 by 2, and it becomes 1. It is a. And then now we want to make it integer. So suppose you want to make it integer 1 by 3, 1 by 2, and 1. So you want to multiply by something. Hana? So now, so if I multiply it by 6, so it becomes 6, it becomes 6, it becomes 6. Hana? And then you will have a like 2, 3, and 6. So this plane will be 2, 3, 6. So suppose in anything I say 1, 0, 0 plane, that it is a plane which is actually just cutting. You can say it is in the YZ direction. Why? Because it is not coming Y and Z axis. So it is a YZ plane. In X direction, it is coming at unit distance. So this plane is 3D. Now, now we come to another important thing. This up to this, the structure is finished. Now we come to a very important thing, that is the valence bond. So now we have silicon. अभी silicon किस form में bond होता है? That is tetrahedral. जिसे see, it is diamond structure. So you have one silicon, and it is surrounded by, you can say, 4 more silicons. Imagine there is one silicon here, and then there are 3 spheres. Bottom mein, there is 1 sphere at the top, and this is the 1 sphere. So there are actually 4 equidistant spheres, silicon. So it is surrounded by 4 such spheres. So it is surrounded by, now because actually it is this you can say 3D visual view, it is 0, 0. You can just imagine like this. You have 3 sphere. This is actually in the unit cell format. So usko every time if you want to visualize, you just visualize 1 sphere and then 4 sphere, जैसे हमने try किया था 2 slides before. Or in simple 2-dimensional you can say view, हम लोग उसको we represent it like that. So we have silicon, 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 4 silicon, and then there's 1 silicon at the enter. Actually, it is like that. आपका ये 3 silicon, ये वाला 3 silicon is like that. Then you have 1 silicon, the center वाला, and then above that there is another silicon. So this silicon, the center silicon, is actually which we have forcefully inserted in the tetrahedral void. So this you all know this part, that this one atom is shared and a bond is formed. This is called as the valence bond, and this is a covalent bond. These are because everything is equal. However, in case of gallium arsenide, we suppose in you can say this is gallium and all these are arsenic structures. If we see that is a zinc band structure. So in gallium arsenide, this bond is actually not, this is not 100% covalent, but a little bit of the ionic character, but mostly that is also covalent bond. That is also explained the covalent bond. So now comes another thing I want to tell. When this silicon atom or this silicon structure is at you can say 0 Kelvin. Let us imagine at 0 Kelvin. Now at 0 Kelvin, all the atoms or all the electrons are there. All the electrons are bound to their atoms, and this bond is there. So there is absolutely no free electron available inside this structure. So electrons are bound in their respective tetrahedral hadron lattice. Consequently, there is absolutely no availability of the electron. Since the electrons are not available, we know from the first or second slide that it is absolutely essential to have the electron in order to have conduction. Now, since electrons are not there, so it will actually not conduct. It's a totally zero energy. If we just leave that, forget the 0 point energy for the time being for this discussion. So we have like at absolute 0 Kelvin temperature, all the atoms, all the bonds are intact. So there is absolutely no free electron are available, and therefore the silicon, which is actually a semiconductor, it will behave like an insulator at 0 Kelvin. However, as you increase the temperature, the thermal vibrations, these break the covalent bonds, and some of the electrons are, you can say, ionized, and they becomes free, and these become, because they becomes free, they can participate in the current conduction. And therefore this is the reason why when you increase the temperature, the conductivity of the semiconductor materials increases. Now this is clear. Now comes a very important thing, is which is energy bands or formation of energy band. So far we have seen different kind of atoms, you must be knowing. Then we see different kind of atoms comes together, they crystallize in different kind of structures. We are particularly interested in silicon, which crystallize in the form of a diamond structure. So now this, for the time being, for few slides, we leave that discussion there itself. Now we come to another aspect, which is imagine another thing. So you have an atom, you have many atoms, because in crystals they are coming together. So for an isolated atom, the electron can have discrete energy levels. For example, the like for hydrogen atom, which is the simplest one, the energy levels for that are given by this particular equation. This everyone of us has studied. So that means what I want to say, you have an atom. So you have an atom, and so electron inside that atom can only attain certain amount of energy, or certain, and or it can reside in certain energy levels. So those levels which are allowed levels for atoms are for hydrogen atom it is this. For different atoms is the value is different. For hydrogen, because it's simple atom, it is more precisely calculated. For other, a lot of approximations has to be made. So now if we you can say this, so for different higher excited states, like for ground state, obviously it will give 13.6 if you put n is equal to 1. If I put n is equal to 2, then I will get minus 3.4. You get n is equal to 3, then I will get 1.51, and n is equal to 4, then this one. By this way, you can go on calculating the energy levels. So different energy level. So what this energy level means in hydrogen atom, the electron which is in the orbit, it cannot have any energy of its choice. It can only acquire if you give from outside either this energy or this energy or this energy or this energy. If you can recall, we studied one such experiment also during our BSc days, when there was a gas, and then electrons of the radiation of different kind of varying you can say wavelengths were passed from one side, and we saw that only certain amount of energies were absorbed. So this I'm talking about, so far I'm talking about the only one atom. So now this was one atom. Now let us see two atoms. I have another hydrogen atom. When they are far apart, the allowed energy levels for a given principal quantum number consist of one doubly degenerate level. Means suppose now okay, I will say consider only like these energy levels. So suppose I have one hydrogen atom here and one hydrogen atom. So I will have one energy level which is corresponding to this hydrogen atom and another energy level which is corresponding to this hydrogen. Now you see this energy value is exactly same. So when you have two states where the energy level is exactly same, this is called as the degenerate state. So now you have a doubly degenerate gases. So you have two atoms and you have exactly two states, but they are far apart. Now problem starts when you start bringing them together. When they are brought closer, this doubly degenerate energy value will split into two levels. So why it will split into two levels? Because of the Pauli's exclusion principle, which says this electron is a fermion, which says that no two electron can have, or in a same system, all the quantum numbers which are same, or the energy level. So and when all quantum numbers are same, it will imply that the energy levels are also same. So that will actually you can say it is not possible because of the Pauli's exclusion. So what will happen actually? So these two levels, which were actually when you will bring these two atoms together, this will actually split into two. So it will not remain same. So what will happen? So this energy level will split into two levels because of the interaction of these two atoms, or you can say the overlapping of the wave function. So this split occurs due to the Pauli's exclusion principle, which states that two electrons in a given system cannot reside in the same energy state at the same time. This is a very important concept when the band formation comes into means when the band formation is taking place inside solids. Though it is not hydrogen, but it is for the other thing. So I hope this is clear to all of you. If it is not clear, just ask me right now. So now we have seen that different atoms comes together. We, for our convenience, when we were explaining the crystal structure, we presume that all the atoms are spheres. They come together. They crystallize in certain amount of crystal structures. The most important structures for our semiconductor part is cubic, or for cubic or a modified cubic, I can say diamond structure because it's a FCC. Oh, I will say modified just for like convenience. Then zinc blende structure also we saw, and then we saw that that at absolutely 0 Kelvin, all the electrons are actually bound. So it's not possible to have any conduction. Then we know very well what was the structure or what were the energy levels of a pure silicon atom. They are discrete and they are very sharp. Now we have come to another concept which says if we bring two atoms together, as far as they are far apart, there is absolutely no problem. But when we bring them together so that their wave function overlap, or they are interacting, or they are part of one system, in that case we cannot consider them two separate entities, and therefore the electron which is residing in their outermost orbit, two electrons cannot have the same energy level because they're the part of one system now, and therefore they must have different energy level. In order to follow this principle, the energy level or that degenerate energy level, it splits into two levels. So this is a very important concept. Now we will go ahead and see how actually the bonds are formed in a solid, and that too qualitatively. So far we have seen only 2 atoms. Now let us imagine many atoms. Many atoms means, see, can you imagine how many atoms are there in solid which you are having in front of you? Any solid, just see. Suppose let us see 1 centimeter by 1 centimeter by 1 centimeter of silicon cube you are having, you are putting in front of you, and suppose the density of that silicon is around 2.4, something like that. So 2.4 gram is the weight. How many atoms you may be having? I tell you, it is order of 10 to the power 23. So imagine 10 to the power 4 is 10,000. 10 to the power 5 is 1 lakh. So that way 1 lakh, 1 lakh, 1 lakh, 1 lakh, 1 lakh, multiply all them. So you will be having so many number of atoms in that particular 1 centimeter by 1 centimeter by 1 centimeter cube of silicon. Now, when they were far apart, there was absolutely no problem. Problem starts when you have brought them together and made them part of one system only. So there is a problem now. What are those problems? Let us go one by one. So if now n isolated, n means, imagine in this one, in this example, 10 to the power 23. It is lakh times 1 lakh. So now n isolated atoms are brought together to form a solid. The orbits of outer electrons of different atoms overlaps and interacts with each other, as in previous slide I tried to explain with the hydrogen atom. This interaction, including those forces of attraction and repulsion between atoms, their nucleus, different you can say different electrons. So there is all this amounts to cause a shift in the energy levels. So now, instead of 2 energy levels, as we saw in the case of hydrogen in previous slide, there will be now n separate but closely spaced levels will be formed. So I will be having now, there were, suppose it was a some certain element X, which when it was far apart, this energy level was this, the maximum energy level. Suppose for hydrogen it was 13.6, for other it will be somewhere else. And now when you bring together at this point, it is start you can say the wave functions start overlapping, and therefore it starts splitting. And when this X atom crystallize at this distance, which is actually interatomic distance A. So now you will see this is splitting. This is at this side it is atomic interatomic distance. So when it come like this, so if it is interatomic distance, so you will have actually the single level which was looking like this. Actually, you will be having n degenerate states. Those all combine together and form a band. So instead of 2 levels, you are having now n separate, but these are not like this. So it is, I am showing like 1, 2, 3, 4, 5, 6, 7, 8, 9, imagining that there are only 9 atoms. But as I said you, 10 to the power 23, first thing you have to imagine how big 10 to the power 23 number is. Can you imagine it? If you start imagining, you will realize that it's a too huge a number, that actually it will be almost continuous band of energy. So if you start separating this much into 10 to the power 23 equi-space lines, you will realize that you will find almost continuous level. So this is called as the band of energy. So this band of n levels can extend over a few electron volt, like from here to here. It may be few electron volt. So here it was precisely, you can say exactly 1. There was no so no broadening here. So this band of n level, it can have like few energy broadness, And so this is another very important concept. You should always remember this. The electrons now can no longer be treated as belonging to their parent atom. So I was having this atom X. This atom X has one electron. Now I have brought all 10 to the power 23 or n electrons together. Now I have formed a system. So this atom, this electron, which was actually of this particular X atom initially, now under this situation, when I have crystallized it at this interatomic distance and it is here now, so this electron is now, it doesn't belong to this particular X, but actually it belongs to the entire system as a whole, or entire crystal as a, if we start imagining it as a crystal. Okay, if you have understood this, you have understood the formation of energy band. So okay, now we will just see a similar kind of thing in the silicon. I am repeating so that you should not forget it. So this is a silicon atom, we know. So silicon has 14 atoms. So these are arranged like this. And there is one more thing, just realize this gap is different because the first orbit is, there is a, it is not, you can say, uniform gap. As you are going to outer side, the gap increases. Just this is only for picture. So an isolated silicon atom, it is having 14 electrons. Out of these 14 electrons, 10 occupy deep lying energy levels, and whose orbit radius is much smaller than the interatomic separation of the crystal. So when we were bringing all those atoms together, see there is the outer orbit distance was actually comparable to the interatomic separation, and therefore they started interacting with each other. But like the inner orbits, which are actually very, you can say, much smaller. Actually, it is in the orders. It is not exactly. So suppose the outer orbit is 10,000 kilometer, the inner orbit may be having only 500 kilometers. So there is a huge difference in this. Actually, kilometers, I am just telling to give an example. It is not in kilometer, so don't take it otherwise. So it is like that the outer orbit is actually far, very far, and the inner orbits are actually very close. The 4 remaining valence electrons are relatively weakly bound and it can be involved in the chemical reactions. So the 3s subcell means the outer one. So it is having actually n is equal to 3 for 3s, and s is equal to l is equal to 0 because it's s. So it is having 2 allowed quantum states per atom. And 3p subcell will be having n is equal to 3 and l is equal to 1. So it will have actually 6 allowed state. Why 6? Why there 2? Because n is equal to 3, l is equal to 0. So m can be only 0. So then the 4th quantum number, which is a spin, it can be either plus half or minus half. So there is only 2 possibility. So n is equal to 3. Now m, l is equal to, have to be 0, and then the spin, one will be spin up and another will be spin down. So there can be only 2 states here possible. Now if we go to 3p state, so here l is equal to 1, so m will be minus 1, 0 and plus 1. So corresponding to each, you will have up and down, up and down, and up and down. So you will be having 6 states here. So you will have like 2 states here and 6 states here. And how many electrons are there? There are actually 4 electrons. So what will happen? S is having lower energy, so 2 will be taken by this S, and now there are 2 electrons are left. So now it is minus 2, so it is only 2 electrons. these 2 electrons will go into P. So P is actually can occupy, means P has actually space for 6, but it is having only 2. So 4 are actually vacant. Now let us see in slightly in a different way. Now this is here we are at infinite distance. So we have n isolated silicon atom. This distance is now infinite. Now you start bringing them together. So it is like, so as we say, there were actually 3s state and 3p state. 3 state is when I was having single, so this 2 electron, single atom I'm talking about. So 2 electrons were there in this 3 state and 2 electrons were there in this p state. So if there are n, you simply multiply by n, because those n silicon atoms are actually, you can say, non-interacting and independent. So you will have 2n electrons in this state, 3s state, and 2n electrons in the 3p state. Now you start bringing them together. So as this 3s and 3p band grow, they merge into a single band containing 8n state. As the equilibrium interatomic distance determined, now you are actually slowly bringing them together. As you bring them together, now all the atoms are actually at this particular point when they start splitting. That shows that they have actually started interacting with each other at this particular point. Because now it is no longer a you can say a single atom entity. Up to this place, there was absolutely no problem. All atoms were behaving absolutely in the atomic form. As soon as they come at this point, that what is the physical significance? Iska physical significance kya hai? See, I will ask that in the assignment. So इसका physical significance क्या है कि suppose मैं इसको crystallize करूं this silicon को और इस तरीके से crystallize करूं कि जो सारे atoms हैं, diamond structure है भी, जो difference है, the difference is this. So if this difference, all the silicon atoms are this much different to each other, in that case, what will happen? That this will start interacting, and you, in place of like 2 you can say levels, you will be having slightly this kind of level. Just imagine this. Now if I further bring them all the n atoms together, so that the distance between each atom is reduced to this level. This level. So in this process, this will further start splitting, and if I see here, so there will also be, you can see there are 2 bands. One is this band, another is this band. So if I further reduce this, so and at this interatomic, if I make a solid of this much, this particular interatomic spacing, in that case, actually there will not be 2 levels. However, there will be only one energy band which is having this much of the width. So this is y-axis is the energy axis. So you have this much bond. So now what will happen? So when you have 2n this electron and 2n this electron, so there are 4n electrons. So here actually 2n electrons were there, 2 electrons were there, and now in this case there is actually 4n electrons, but those 4n electrons will occupy this, the lower 4n level, and this 4n level will remain empty. But what will happen? In this condition, suppose we suppose I allow or I give little bit of the energy to this particular electron, which is having this much energy, this will be able to accept because there is an energy level which is just above this and it is an allowed energy level. So in that case, this metal, this material will behave like a conductor because you can give any amount of energy, you can apply any voltage, and the voltage or the energy of this electron will be raised accordingly. So if silicon was crystallized at a, you can say, at a distance where the interatomic distance between all the silicon atoms was this much, in that case, silicon should have behaved a perfect, you can say, metal. But that is not the case. So now we further come here. If we reduce the distance between these atoms, in that case, what will happen? After this particular spacing, this further splits into two different bands. Now, here there are only 4n states, and at this also there are 4n states. Now, what will happen? These electrons will occupy the lower one because you always, every you can say electron, try to occupy the lowest possible energy level if it is allowed for it. So now I directly come to this point, which is the actual or real point for the silicon, where the interatomic distance is 5.43 angstrom. And at this point, if you say the atoms which were silicon atom, which was having this 2n or 3s energy level and 3p energy level, see 3s and 3p energy level will be discrete here. So those 3 and 3p, they have actually, you can say, combined together and form this kind of bands if there are 3n atoms. So this width of, like, it will be like for means 3 or you can say n equidistant energy levels lying in this band. So you are having now so now you are having this 3n electrons, 3n multiplied by 2. So 2n is this, so 3n multiplied by 2 states were there. So now you have actually 2n electrons which were in p state and 2n electrons which were in actually S state. So there are 4n electrons and the 4n energy levels here. So all those 4n electrons will occupy these levels, and there will also be 4n energy states which will be available here, but there will not be any electron there. So there will be a gap. Only the electron from this point to this can reach, provided if you give this much amount of energy. Understood? So this is gap, the band gap, which is 1.12 electron volt. This is the conduction band. This is called as conduction band, and this is called the valence band. Now, if in a hypothetical situation, suppose the silicon, which has actually crystallized with the lattice parameter as 5.43 angstrom, suppose वो 3 angstrom और यहाँ पे crystallize हुआ होता उसका, in that case the gap would have been much more. The okay, conduction band was here, so this energy gap would have been different, and similarly the जो width है band की, that should also be different. तो अभी आपको, you must have understood how the bands are formed and how the bands are formed in the silicon. And if silicon is crystallized at a different, silicon in a gaseous state or silicon in isolated state is different than when silicon is, you can say, made a crystal with a diamond structure. They are brought together. When the crystal is formed, in that case, how its, you can say, energy levels or the presence of the electrons in different energy levels is different than that of the atoms. So how the material behaves differently than the uh, behavior in its atomic state. Now, if you go back and try to answer that question, that why gold atom, when it is a single atom, it is not conducting, but why when it becomes a solid and it becomes a crystal, then it starts conducting. Similarly, for every atom, like copper also, silver also. Probably the question which I asked in first or second or third slide, why those are not conducting, now you will be able to answer. So when they come together to each other, they form the band, and then there must be something. There may not be actually a band gap there, and therefore they may be able to conduct. So now let us continue on this only. So at absolute 0 Kelvin, see the electron occupy the lowest energy state, so that all states in the lower band will be full and all states in the upper bands will be empty. So all these, as I already explained, these will be totally filled and this will be totally empty. The bottom of the conduction band is called EC, which is this bottom of the conduction band. This is the EC, and the top of the valence band is called as the EV. The band gap energy, which is EG, that is actually, you can say, difference of energy between these two levels is called as the band gap energy. So physically, actually, if you try to understand it physically, this is the energy, the band gap energy, which is required to break a bond in the semiconductor, so that an electron which is actually bonded, that is you can bring it there in the conduction band. If you can give somehow 1.12 electron volt to an electron, then it will go into conduction band, and then there are a lot of, you can say, energy levels, it will start conducting. Now we come to how much time is so maybe so I think we can stop here, and we will continue in the next lecture. If you are having any question, any doubt, please ask me. I'm ready to answer. I request you to just think about this formation of energy bands. Though we have taken a little longer time, but it is useful. कोई क्वेश्चन नहीं है? Yeah, I can see Sayanthini, which say no, silver atom cannot conduct. Yes, I agree. But now can you answer why silver atom can conduct? Why silver conducts? I think she has left. Must have. Okay, so since there is no question, so let us close this for the day, and see you in the next class, where we will continue the semiconductor physics. This is important, and I suggest you to understand and try to think actually. Thank you.